clearly for a difference amplifier, which is supposed to compute the difference between two input sources, you need two voltage sources. And then there'll be a bunch of other resistors. Let's draw the circuit. So those are the two voltage sources. Okay, so this is our non-inverting input. Non-inverting input will feed back the output to the inverting input. And then we'll connect this end to a ground through a resistor. Okay, so let's say this is R1, which is R1, R2, R3, R4, P out. Yes, so we are trying to figure out the compute V out as a function of V1, V2, and of course the resistors. R1, R2, R3, R4. Yes, I'll basically redraw this and then we'll do a similar calculation like we've done for the other circuits. Okay, so let's start drawing the currents. Let's just assume that current I1 flows through the voltage source V1 and I2 flows through V2. Now we know that the current flowing inside the amplifier, the V minus and V positive, is 0. And so instead of trying to write another value for the current here in this branch, just to save myself time, I'm just going to write the same current here because of the fact that the current here is 0, right? The current in this branch and also in this branch, I plus equals I minus equals 0. So just that clears off a few more equations for me, so it makes it easy. Okay, so if I2 is the current in V2, the same current will flow through this. Yeah, I've reduced the equations by 2. Okay, now this one is V minus, let's say this one is V plus. And just to, maybe I should just write it the right place. This is this point. Redraw this. This is V minus, and then this is V plus. Okay, so I think I'm all set to try to find that functional relation between V out and V1 and V2. Okay, so let's start with, I think the easiest thing is to start with the assumptions of an op-amp. V minus equals V positive. Op-amp assumption. Okay, then we can try to find an expression for I1. So V1 is the voltage here. This seems to be V minus. And then the difference, the potential difference between V1 and V minus is the voltage drop across the resistor. So V1 minus V minus equals I1 R1. Then we have, similarly, we can write V out is the voltage here. V minus the voltage here. Now, one thing to note is that the direction of the current flow is from V minus to V out, right? That's the assumption. So you want, so V minus is at a higher potential. So what I'll do is I'll write this as V minus minus V out equals I1 R3. Okay, so we've basically exhausted the equations for I1. Let's try the equations for I2. So V2 minus V positive, which is the voltage here, should be equal to the voltage drop across R2. And then finally, V plus is at a higher voltage than ground. So V plus minus 0, which is the ground, equals I2 R4. Okay, so let's count the unknowns. Okay, they are V minus, V positive, I1, I2, and then V out is an unknown because we are trying to compute V out because we are told to find that as a function of V1, V2, and so on. So V1, V2 are known. So there are 5 unknowns. Okay, but we have 1, 2, 3, 4, 5. We have 5 equations. Okay, so if you have 5 equations, 5 unknowns, you can solve for the unknowns. In this case, we are really not interested in V minus, V positive, I1, I2. So you can eliminate them. So for example, you could, how could you do this? You could eliminate V plus from this and that equation. You could eliminate I1 from these two. You could eliminate I2 from these two. And then the net equation will be only in terms of V plus or V minus, depending on what you eliminate. So you can then eliminate the resulting questions from the top 2 and bottom 2. So that, I believe you can figure that out. I'm just going to write the final expression for V out as a function of V1, V2, and the resistors. Solving for V out, we have V out equals R4 divided by R3 plus R4, 1 plus R2 divided by R1 times V2 minus Okay. It's very complicated, looks very complicated. And then it's also looks like, it doesn't really look like it's going to give us the difference between V2 and V1, right? It is something we need to work with the resistors so that it gives the difference. Can anybody see how you can make this V out proportional to the difference? You have to choose the resistor values, R3 and R4, such that this will give you will be proportional to V2 minus V1. Okay, so you could possibly do that, but I'm going to make it slightly easier for you to see that by doing this, this sort of substitution. So what we'll do is we will basically ask ourselves, what do we really want? We want V2 minus V1. That should be our input. So let's call that VD for the difference. And let's call the average as VCM. In other words, it's 2 VCM. I'm just doing this sort of trick just to make our life easier. I'll try to eliminate V1, V2, try to write in terms of VD and VCM, VCM being the average, and then we'll try to find relations between the resistors that we get what we want, which is the difference. Okay, so we can solving for V1, V2. That is, from those two equations, we can write. So for example, if you sum the two, you'll get V2. If you subtract first from the other, you'll get V1. So doing that, we have V1 equals 2 VCM minus VD divided by 2. And V2 equals 2 VCM plus VD divided by 2. Okay, so what we'll do is now we'll take, let's call this number 2. We already have an equation for V out. Let's call this 1. So we'll substitute two in 1. And that will give us like a fairly big expression, which looks like this. V out equals R4 divided by R3 plus R4. 1 plus R2 divided by R1. Now we had V1 here, so which I'm going to substitute with what we got here, V1. That's, oh, I did. It was V2, I think, not V1. It was V2. So V2 is 2 VCM plus VD divided by 2. And then we had minus R2 divided by R1 times V1, but V1 is what I had over there, 2 VCM minus VD divided by 2. Okay, now there is an exercise which I will again sort of skip, which is I'm going to then try to collect all terms in VCM together and all terms in VD together. Again, you can see that's fairly easy to do because you have that sum. You can just plug in, figure out the coefficient of VCM in the two expressions, put it together, and same for VDM. So simplifying get V out equals 0.5 R4 divided by R3 plus R4, 1 plus R2 divided by R1 plus R2 divided by R1. All this is the coefficient of VD, the difference, and then the coefficient of the sum, the average, is R4 R3 plus R4, 1 plus R2 divided by R1 minus R2 divided by R1 times VCM. Okay, so remember that VD is V2 minus V1, VCM is V1 plus V2 divided by 2. Okay, now I think we are in a position to figure out how to make this look like a difference amplifier. What we're interested in is we want V out to be proportional to VD, and we want VCM, anything before the VCM, to be 0. So what we need to do is we need to be able to set this term 0. Okay, how we can set it 0? it's not magical. You need to choose some resistor value such that it comes out to be 0. So if you choose, if you make this choice, see, if you make the choice maybe R1 equals R4, and then R2 equals R3, so if choose R1 equals R3 and R2 equals R4, then you'll see that the numerator over here will cancel with the denominator here, and then this you'll get ratio of R2 and R1, which will cancel. There'll be R2 divided by R1 here. So this will reduce to R2 divided by R1, and then that will cancel with the R2, R1, and then you'll effectively get 0 here. This will be 0. Okay, so we all set. We have a value for V out, which is, I'm just going to put R4 equals R2, and then R1 equals R3 in the first term also, and you will end up getting R2 divided by R1 VD, which is nothing but R2 divided by R1 V2 minus V1. Okay, and note that this depends on, this is true when R1 equals R3 and R2 equals R4. Okay, when those two, this condition is true, that's true. So if you look back at the difference amplifier, what I'm saying is R2 should be equal to R4, and R1 should be equal to R3. Now, there's something about resistors, which is, if you look at resistors, you will see that the resistors actually have like a variability in them, right? So you'll have the silver or the gold band. So you cannot assure that the resistances would be whatever it says based on the first 3 bands. The other issue is that as resistors get heated, the resistance will change with time because it's get heated. And if that happens, then effectively this term in the bracket will not go to 0 because the resistors are not perfectly matched. So even when VD equals 0, this term, which depends on perfect matching of the resistors, may not actually go to 0, which means that now your V out will be something which is non-zero. And that's not good because now your circuit is saying that the difference, which is supposed to be 0, is actually non-zero, right? So it tends to be very sensitive to this choice of resistors, and that's why a difference amplifier is never really used. So this circuit, which I showed you, physically, it's not constructed and used in a circuit because of this problem. That is, the perfect matching is just hard to do. So what people do is they basically use what is known as an instrumentation amplifier. And I'll draw the circuit. It's a bit more complicated, so I will not go through the derivation of the instrumentation amplifier, but an instrumentation amplifier is used in place of a difference amplifier. So we just write this down before I move on. Since this is based on perfect matching of resistors, that is R1 equals R3 and R2 equals R4, this circuit is sensitive to this matching if the resistance changes with time. An example of that change would be heating. The example would be resistance increases as the resistor is heated. This circuit will not be useful to compute the difference. Okay, so hence this is not used for computing the difference. And so what is done is an instrumentation amplifier is used to compute the difference.